Classifying critical points, part 3. Using the second derivative to figure out if critical points are local maximums, local minimums, or neither. So if we want to use the information from the second derivative to talk about critical points, that means that we are likely going to have to calculate the second derivative if we don't already know it. So consider the function f of x equals 4x cubed minus 6x squared minus 72x plus 12. Now, we know from earlier that the first derivative is 12x squared minus 12x minus 72, and if we factor that down, we get critical points at x equals 3 and x equals negative 2. But how can we use the second derivative to determine if these critical points are local maximums or local minimums? So remember, if the second derivative is positive at a point, then f of x, the original function, is concave up at that point. And if the second derivative is negative at a point, then the original function is concave down at that point. So that's describing what the original function is doing. And we had tests using the original function that we can map directly to the second derivative. So if we plug a critical point into the second derivative and it's positive, that means that the original function was concave up and that critical point would need to be a minimum. Now, if we were to plug our critical point into the second derivative and it was negative, that means the original function was concave down, and that would make your critical point a maximum. Let's look at what happens here. So the second derivative of this particular function is going to give us 24x minus 12. Now we need to plug in each of our critical points to see what happens. So first let's plug in 3. So if we plug in 3 into the second derivative here, we're going to get 24 times 3 minus 12, which is going to give us positive 60, which means that when x equals 3 and we're at our critical point, the original function is going to be concave up because it's positive at the second derivative. And if it's concave up, that means that x equals 3 is a local minimum. Similarly, if we were to plug in negative 2 into our second derivative, we would get 24 times negative 2 minus 12, which would give us negative 60. If the second derivative is negative, we're going to be concave down at that point, and therefore negative 2 is going to be a local maximum. So when we take these ideas about concavity and we pair it with what we know about critical points, we're able to come up with the second derivative test. Let's see how that's written. Suppose that P is a critical point of f of x. If the second derivative is positive at P, that means that the original function is concave up and that your critical point is a local minimum. If the second derivative is negative at P, the original function is concave down, and therefore your critical point is a local maximum. And if your second derivative is 0 at P, that means that this test is inconclusive, and you should do one of the other tests to determine if you have a local maximum, minimum, or neither. Now, of all the tests, this one's a little counterintuitive, because again, if your second derivative is positive, that's going to equate to a minimum. And if it's negative, it's going to equate to a maximum. So this is a really important one to keep straight as we test our different critical points. So let's look at our examples. Example 1. So we had 3x squared plus 6x plus 1. And we want to use the second derivative test to determine if the critical points are local maximums, minimums, or neither. So my first derivative was 6x plus 6. And I was able to use that to find my critical point is negative 1. If I now go ahead and calculate my second derivative, the derivative of 6x plus 6 is 6. Now, it's a little strange because I don't actually have an x to plug negative 1 into. However, the second derivative is going to be 6 for every single point, which means the second derivative at 1 is also 6. So I can still use this test. Since 6 is positive, that means that the original function is concave up, which means that x equals negative 1 is going to be a local minimum. And again, I know it's a local minimum because my second derivative is positive at x equals -1. Let's try another. Suppose that f of x equals 2x cubed minus 3x squared minus 36x plus 14. Use the second derivative test to determine if the critical points are local maximums, minimums, or neither. So our first derivative is 6x squared minus 6x minus 36. From there, we're able to find that the critical points are x equals -2 and x equals 3. Now, to use our second derivative test, we need to find the second derivative of this function. So here, that's going to give me 12x minus 6. Now that I have my second derivative function, I need to plug in each of my critical points. So let's start by plugging in -2. If I plug in a -2 here, I'm going to get -30. So if my second derivative is negative at a point, that means that the original function's concave down, so I know that -2 is a local max. Similarly, I can test my other point the same way. So if I plug in a 3 into the second derivative, I get 12 times 3 minus 6, which is going to give me positive 30. If my second derivative is positive, that means my original function is concave up, and my critical point is a local minimum. So I have a local minimum at x equals 3. So I'm able to classify my critical points by observing what the concavity is at that point. Now, the last two examples, the derivative was relatively straightforward, so the second derivative test was a good idea. But for the next couple of examples, we'll see how difficult the second derivative test can be if you have to take the second derivative of a tricky function. Example 3. Suppose that f of x is x squared over x minus 2. Use the second derivative test to determine if the critical point of f of x is going to be a local max, a local min, or neither. So remember, our first derivative, once we simplified, was x squared minus 4x, all divided by x minus 2 squared. We're able to find critical points at x equals 0, x equals 2, and x equals 4. If we want to find the second derivative of this function, we're going to have to use another quotient rule, where we set f equal to the top of our function, which is x squared minus 4x, and g equal to the bottom of our function, x minus 2 squared. From there, we need to find each of their respective derivatives. So the derivative of x squared minus 4x is 2x minus 4. In order to find the derivative of g, we need to use a chain rule, where our z here is going to be x minus 2. So our dz dx, the derivative, is just going to be 1. So the 2 comes down, and we subtract 1 from the power, and then we multiply by 1. But if you multiply by 1, you get the same thing back. So then, for our quotient rule, we're going to do f prime times g, which is this term here, minus g prime times f, all divided by g squared. So if you square something that's squared, it's now to the 4th power. So once you have your second derivative, you want to plug in each of your points to determine if they're local maxes, local mins, or neither. So if we plug in a 0, it all crunches down to -16 over +16, which is going to give me a -1. So if your second derivative is negative, that tells you that the original function was concave down and that your critical point is a local max. So x equals 0 is a local maximum. If we try the same thing with 4, and you plug a 4 in carefully everywhere on the top and the bottom, you end up with 16 over 16, which is +1. If your second derivative is positive, that means the original function is concave up, and your critical point is a local minimum. If we tried to plug in a 2 into our function, on the top we're going to get 0, and on the bottom we're going to get 0. So that means that our second derivative test is inconclusive at 2, and we need to use a different test to determine if it's a local max, a local min, or neither. Earlier, we graphed this function and we determined that the critical point at 2 was neither a max or a min. So you can see here that the second derivative itself is not easy to compute, so it may not be the best test to use when you're classifying, but it can be done. Let's look at another tricky one. Example 4. So if f of x equals x cubed times 1 minus x to the fourth, use the second derivative test to determine if the critical points are local maxes, local mins, or neither. So we determined that the first derivative, once it's simplified, is x squared times 1 minus x cubed times 3 minus 7x. From there, we were able to get the critical points of 0, 1, and 3/7. So if we wanted to take the derivative of this function, we'd have to do a modified product rule. So it's a product rule, but then there's a product rule within the product rule. So I picked my f to be the first two terms, x squared times 1 minus x cubed, and my g to be the last term, 3 minus 7x. Now my g prime is just the derivative of g, which is negative 7. That one's straightforward. But to take the derivative of f, I have to do another product rule. And so I took the derivative of the first term to get 2x times the second, plus the derivative of the second times the first. But when I took the derivative of the second term here, I had to use a chain rule. So it was really quite complicated to get the algebra down. So then I have to do f prime times g. So my f prime is in this whole first bracket. It's this whole term that came out from the product rule times g plus g prime times f. I'd pulled the negative to the front to make it a little bit easier to see, but as you can tell, it's already a very complicated function. Now, once I have my second derivative, again, I want to plug in my critical points to try to determine if the second derivative is positive, negative, or 0. If I tried to plug in a 0, what's going to happen here is that this term, first term, is going to be 0. This term is also going to be 0 because of the x squared, and it's multiplying this. So this whole first part here is going to be 0 minus, and then this term's also going to be 0. So when I plug in a 0 into the second derivative, I get 0. So the test is inconclusive. Now, if I tried to plug in a 1, the same thing is going to happen here. Because the first term, this is going to be 0. This is going to be 0. Over here, this is going to be 0. So everything that's multiplied together ends up zeroing out. So when I plug in 1, I also get that the second derivative is 0 and therefore inconclusive. However, when I plug in a 3/7 really carefully, this term ends up being 0, which is going to zero out this whole first part. But the second term is not 0. Instead, I'll have 1 minus 3/7, which is positive. Something positive cubed is positive. X squared will be positive. So I have 0 minus something positive, which is going to give me something negative. So when I plug 3/7 in, I do get some sort of answer. I get that my second derivative is negative. And we know that if the second derivative is negative, that means that your critical point is a local maximum. So this type of problem, it's not really ideal to use the second derivative test. There are better tests that are easier to work with to determine if your critical points are local maximums or minimums, but it can be done. Although it didn't give us all the information that we needed. We were only able to really classify one point, but it's still better than nothing. So let's look at another situation. A situation where we have a lot of information we have to sort through to try to do some analysis and determine what we know about a function. Example 5. Suppose f of x is a continuous differentiable function. Additionally, we know the following information. So here we have a various amount of information about the function at points, the derivative at certain points, and the second derivative at certain points. And we want to use this information to determine where we think that f of x is likely to have a local maximum and or minimum. So we have to sort through this information to see what we can figure out. So let's look at each piece individually. F of 1 equals 10. So that's a point on your function that when x equals 1, y equals 10. F of 7 equals 1. Also a point. Points aren't generally helpful in helping us determine things like maximums and minimums. Now we know that the derivative at 2 equals 4. So that tells me that my original function, f of x, is increasing at x equals 2. So remember, we're talking about what's happening at 2 because 2 is the independent number that got plugged into the derivative function. The next statement says f prime of 4 equals 0. So that's really important because that tells me that I'm going to have a critical point at x equals 4. So remember, the x value is what's inside the function. So when we're talking about where things are happening, we're pulling the number that's inside f, not the one that it's equal to. Because when it's equal to something, that's giving you the slope of the tangent line when we're talking about the derivative. So f prime of 9 equals 0 means we're going to have a second critical point at x equals 9. Now I'm also told that the derivative at 12 equals 8, which means that my function is increasing at x equals 12. Now I have that the second derivative at 4 is negative 4. So if the second derivative at a point is negative, that means it's concave down. So I am concave down at x equals 4. And then I have that the second derivative at 9 equals 3. So if the second derivative is positive at a point, then I'm going to be concave up at x equals 9. So again, it's at 9 because 9 is the independent value that's plugged in here. So looking at the big picture now with all the things I know, I'm really interested in what's happening at the critical points because I know that that's where I'm likely to have local maxes and mins. So I have a critical point at 4 and a critical point at 9. But then I also have information about the second derivative at those points. So at 4, my function is concave down. So if I have a critical point at 4, and I know that the second derivative is negative there, and I'm concave down, that tells me that x equals 4 is going to be a local maximum. Similarly, I have a critical point at 9, and I also know that I'm concave up at 9 because the second derivative is positive there. So that tells me that x equals 9 is going to be a local minimum. So we have all the information we need to talk about where these things might happen, these local maxes and mins, but we have to sort through all the information we have and figure out what's relevant and just use those parts. The other statements here give us a little bit of information about the function, but not really about the critical point. So we have to determine what's important to use. Example 6. Suppose that f of x equals ax squared plus bx minus c, where a, b, and c are non-zero constants. What has to be true about a for this function to have a local minimum? So we talked a little bit about this function before, but let's recap. Our first derivative of this function is 2ax plus b. So if we want to find the critical points, we would set that equal to 0, and we get x equals negative b over 2a. But that just tells us about critical points. It doesn't tell us about whether it's a maximum or a minimum. And since we're in the second derivative test section, let's look at the second derivative to see if it tells us anything. So here, the second derivative of this function is going to be 2a. Well, that's really interesting because the x has disappeared, which means that this entire function is either concave up or concave down based on the value of a. If a happens to be positive, greater than 0, that means the entire second derivative is positive, which means for all values of x, your original function is going to be concave up. Whereas if a happens to be negative, that means that for every value of x, the original function would have to be concave down. Here, we want to know what has to be true about a for this function to have a minimum. So if this function is to have a minimum, we would need the second derivative to be positive so that the original was concave up. So a would have to be greater than 0 in order for this function to have a local minimum. And then we also know that it's going to happen at x equals negative b divided by 2a.